Hello everyone, my name is Tiago and this is my PhD presentation that I delivered in my defense at the University of Parma. My advisor was Marco Locatelli and my co-advisor was Manuel Iori. And this work also had a collaboration with Mairo Moreira from Brazil and José Fernando from Portugal. Our work is entitled Algorithms for Cutting and Packing Problems. Okay. Well, we addressed two main problems, so I divide my talk into two main parts. The first one is related to the pallet building problem, the second one to the rectangular cutting problem. And for each part, I will discuss these topics, okay? Let's start pallet building problem, or PBP. For this problem, the proposal arose from a real-world application subject to non-trivial constraints. And the idea came from an Italian company for automation of production processes. I highlight that we didn't have a partnership with this company. They only gave us their database to develop our research. Well, about the process, they consider several ones, but our interest is in picking and packing. What is this? This is the task of creating pallets from individual 3D items. This problem is also called distributors pallet loading, where pallets are formed by boxes from different customers, because in general, a single customer cannot afford the whole pallet. And it's required a proper packing that speeds up load-unload operations. But why do you need a proper arrangement of items? Let me give you an example to understand, to explain this situation. This man must unload a simple pallet as soon as possible. And he must transport similar items to different places. So he should use this machine to transport items. So this transfer machine he can use to transport items. And we have two cases to analyze. The first case, the pallet is composed of items in this disposition. Items of the same color are contiguous. It's very easy to unload this pallet. Now consider the second case. We have the exact same items, but in a different disposition. Since items are not contiguous, he needs to go around the pallet to unload 4 items. Additionally, he might not see the item in the middle of the pallet because it is surrounded by different items. So it's harder to unload this pallet. Therefore, this simple case shows us how important it is to place items in a proper arrangement according to specific needs. Okay? Great. So now let's start building a pallet to understand the whole problem. A pallet has a base and it's created by placing boxes on there until it's filled up. We also could create a pallet with different boxes in this way, for example. But which one would be the best? In most cases, we don't know the answer, but we have the conditions to do that, which are all items should be placed on a pallet in such a way that the constraints are fulfilled and the number of pallets used should be as low as possible. So the key is to understand the constraints of the problem, okay? So let's do that. The first constraints regard the basic ones, and we address 3 of them. No overlap, items delimited by a space and rotations. We also address more complex constraints. Fill factor relates to the required utilization percentage of a specific surface. These cups, for example, represent different fill factors. And stackability relates to the item disposition on pallets, which restricts how the box can be placed on the top of each other. And practical constraints, but before presenting them, I explain the family concept to separate items. Family is the generalization of a concept, a practical example, the glass family, while type is its specification. For example, mugs, cups, wine cups, objects made of glass. Okay, but why is this concept important? There are several reasons. First, it allows to divide the pallet in smaller parts by using layer levels with items of the same family. This pallet, for example, is composed by 3 levels. This division simplifies the algorithm to create pallets. But why do you place items of the same family on the same layer? Because it emulates the stability constraint, since items of the same family have similar height and weight, not necessarily equal but very similar. So, to avoid this situation, an unstable pallet, layers composed by those items tend to create a stable pallet like this one. Of course, this introduces simplification of the real weight that an item has to bear in a load. However, this simplification is widely adopted in the literature as it works well in practice, right? So, based on the layers composition, we classify them into types. First, single item layers composed by items of the same type and same family, which is represented by a color in this figure. Single family layer composed by items of the same family but different types. And an exception, each pallet may have one layer and only one composed by multiple families. And this layer is called residual layer. That said, the family concept defines the layer's disposition. First, items of the same type must be contiguous. Second, at least one item of a group must be visible from the border. I give you an example. Considering these figures, the first two meet both requirements, as we can check. On the other hand, the last two fail to meet at least one of them. Of course, this constraint is item dependent, in which is required at least 2 items of the same type. And finally, the types of layers define the pallet disposition. The first part is formed by the most stable layers, the single item layers. Next, layer composed by different types but the same family, the single family layers. Last, one layer to complete the pallet, the special residual layer. That's it, the problem is defined. To solve problems related to the PVP, the literature presents several approaches. This survey in bold presents a collection of state-of-the-art packing strategies. It's very common to use constructive heuristics. For example, this paper in which we base our algorithm on two-step strategy. First layer and then pallet is frequently applied for heuristic algorithms. Regarding heuristics to deal with 3D items, this strategy is the closest to ours in this working boat. However, the goal of all presented papers is only optimize the fill factor of pallets. Therefore, we propose to go beyond that goal by meeting the contiguity and visibility constraint. To achieve this, we propose 4 main strategies, these ones, and all of them use the two-step heuristic to create a solution, creating first layers and then pallets. Okay? Now I will go into detail for each of them. The first solution method is our base heuristic algorithm called EPMH, which is an adaptation of the extreme point heuristic with evaluation functions to create layers and a grid heuristic for generating pallets. This heuristic is deterministic and has no local search methods. In details, first, extreme point heuristic. Given an item k and a partial solution, we should pack k. To do that, we use one of the feasible points called extreme points. So I select one of them and place the item there. Then remove this point and new extreme points show up. in the next iteration, all these points will be considered. However, which extreme point should I choose, since the algorithm must meet the practical constraints? So we adapted this heuristic to analyze points. For example, to meet the visibility constraints, we must place k such a way it touches the border. So given all these extreme points, only the black point should be feasible. The same goes for the contiguity analysis, and the set of black points is updated, right? Now, given feasible extreme points, which one is the most suitable? So we use metrics to evaluate each of them when placing the item in that point, and we've implemented this list of metrics, right? Center of gravity. Yes, and the grid heuristic to generate pallets that stacks layers. So it starts from the top by inserting one residual layer, then as many single item layers as possible. Finally, if there's still room on it, as many single family layers as possible. That's it. Regarding the results, I would like to draw your attention to the bounding box function, which shows significantly better results than the other metrics. Regarding the second proposal, we've included in it the graph meta heuristic. Now graph is the previous grid heuristic to create the final palette, and the extreme points heuristic with reactive grasp for creating layers. Its improvement phase is based on an upper bound heuristic, which is included in the graph framework here, in order to launch the improvement phase. Additionally, the algorithm updates the reactive structures at the end of each iteration. Regarding reactive method, it's a probabilistic and dynamic method to select a function that will evaluate an extreme point. For example, given three fitness evaluation functions in the beginning, the probabilities to select a function is equal for each of them. However, during the iteration, these probabilities will change. Suppose the scenario of probabilities at the iteration 1000, so F1 has higher probability to be chosen, right? When analyzing the results for pallets and layers, although the number of layers in graph is greater than the first heuristic here, the final number of pallets is lower than in the first heuristic. This indicates that the composition of pallets is important. So based on these results, we propose the third solution, an EPMH, an algorithm without improvement phase, composed by a mixed approach, which use a heuristic for creating layers and exact algorithm for building pallets. Compared to the previous EPMH, this flowchart outlines the modification, introducing a random parameter to create layers and a mathematical model to solve the pallet building, rather than using the grid heuristic. So basically, this exact algorithm stacks layers by meeting the pallet constraints with an objective function which minimizes the number of pallets. In addition, we tested three different values when considering not an exact but a minimum value of fill factor. These are some of the results of the third proposal, and the improvement was greater than 8% when considering a minimum fill factor value equal to 55%. Finally, we propose, from the best of our knowledge, the first mathematical description for this problem. Additionally, we've proposed new math heuristics based on heuristic and mathematical models. Regarding the math heuristic, its mathematical model is a method for the knapsack problem. However, instead of considering the whole set of items, that method optimizes a subset of items. So we have a solution created very fast through a heuristic. Then the model will re-optimize it considering only one more item. Okay? Regarding the mathematical model, first these constraints are applied for verifying overlap among items. Next, the contiguity is met through these constraints, and these ones because this problem is modeled as a flow problem. Next, the visibility is also met. Finally, the objective function considers the bounding box of the items packed because it favors compact arrangement of items. For example, consider these two packings. The bounding box of the second case has the lowest perimeter. I present the last result for the PPP comparison for the number of pallets. In this case, GraphFull outperformed all other algorithms. When it comes to time consumption, GraphFull is the most time consuming, however, this increase is worth it. I show some conclusions for this first part. First, the mathematical formulation proposed is an important contribution for the literature. Considering parametric configuration for heuristics, the most important are the bounding box as evaluation function, as well as lower fill factor to improve the quality of the solution. Although the combination of heuristic and the mathematical models in the math heuristic improves the algorithm effectiveness, it's difficult to find a fine parametric configuration that generalizes its use. When it comes to future works, we have the following to improve performance. The proposal is including it learning mechanisms to select items, as for example SVN. Another strategy is take advantage of efficient methods for solving parts of the problem. For example, the recent floating cuts method to pack similar items when creating single item layers. Finally, we propose to combine different problems, for example, packing and delivery, to try to improve the logistics of the whole process. Okay? That was the first part, and now I present the second part that is related to the rectangular cutting problem, or RCP. Defining it, the RCP is a cutting problem in which we have only one rectangular plate and the goal is to cut from it a set of items where items have profit and demand. And the objective function here is maximize the total profit from the items cut. That's it. Very simple, the definition, but not the resolution. For this problem, the proposal is to develop a milk model that considers both guillotine and non-guillotine cut types. For this case, the first order non-guillotine cut. To this end, the proposal is based on the idea of floating cuts, a technique that simplifies the regular milk models when reducing the number of variables used, for example. I will explain about this next. Regarding guillotine and non-guillotine cut types, how to define them? It's simple, considering any two-dimensional plate. Guillotine cut means that it's always possible to cut from one orthogonal edge to the opposite one. On the other hand, no guillotine cut means that it's not always possible to do that. Okay? Regarding floating cuts, you don't have x and y coordinates of items as regular milk models consider. Instead, we assume that from a given plate, a maximum number of new plates can be obtained without explicitly identifying their positions. So a decision variable is associated with the size of a cut and not to the position of the cut. as shown here in the figure. And this is the main difference from the well-known one-cuts model from Dikoff, for example, which use a decision variable for item placement. And here the position of an item is based on this division. Regarding constraints, we address only the basic ones as we did previously. And we base this proposal on the following work surveys. I highlight this one to address the classes of knapsack problems. When it comes to models to solve this problem, the tree search was first proposed by Christoffel and Whitlock to solve guillotine cuts. Related to non-guillotine cuts, referred to FICAT. Constraint programming was used for both guillotine and non-guillotine cut in different algorithms. Additionally, pseudo-polynomial MILP models and heuristic solution were also proposed to solve RCP problem classes. However, neither one is flexible enough to address both the guillotine and non-guillotine cuts. Therefore, to cover this requirement, we propose a general inflexible parametric MILP model to address both cut types. According to Voscher, the RCP can be divided in many classes, so we are interested in two of them: single large object placement problem, or SLOP, and single knapsack problem, or SKP. Both classes also have some variants, thus we address these specific ones. First, to solve the problem with no guillotine cuts, we've proposed the 5-arcs model. It's called so because this model is based on the first-order no guillotine pattern, in which a packing is composed of 5 items arranged in this disposition: top left, top right, bottom left, and center. Based on that idea, each piece is represented by a node in a tree where the root is the original plate. Since this is a recursive structure, the division for each piece continues for a predefined number of times, here defined by the parameter h. That's why this is a parametric model. When it comes to guillotine cuts, we propose an extension from the 5-arcs model. The idea is similar, however, we cut a plate in at most 4 pieces. This is done by considering 2 possibilities for cutting it: vertically, then creating the pieces left and right, or horizontally, then creating top and bottom, right? The tree is similar, however, each node has only 4 children. In addition to that, we proposed several valid inequality constraints to strengthen the model. I present only the symmetry reduction for the 5-arcs model. When we refer to a symmetric solution, we mean the exact same solution from another perspective. For example, this is a non-guillotine solution, but rotating it, we have the same solution. Similarly, mirroring it, we have another perspective. Finally, applying another rotation, again, the same solution. So the model must allow only one, and the constraints proposed cut 3 of them, strongly reducing the search space. Now we focus on the results. We've performed preliminary experiments to determine the height of the tree, that is, the parameter h. This is the average result for the non-guillotine SKP, and we concluded that h equal to 4 is the most suitable value, since it was able to find the best average result, while the gap remained relatively low. Okay. Additionally, we've analyzed the impact of the constraints to strengthen the non-guillotine model. Here we conclude that for both problems, SKP and SLOP, the constraints included strengthen the base model with a large positive impact on the solver gaps. Finally, we analyze the model's performance in comparison to the state-of-the-art formulation for guillotine cuts. When it comes to SKP, this part, the model proposed outperformed the literature approaches when solving 24 24 instances optimally. However, when it comes to slope, the number of optimal solutions found was lower, only 33, although the average for the gap is still low, lower than 0.5%, which is not the case when we analyze the gap in the literature for the SKP greater than 12%. Okay. Well, our conclusion for the second part are floating cuts technique can be used effectively, providing several benefits, and flexibility is the key word, in addition to be competitive in most cases. Regarding future works, I highlight our new research on floating cuts. Now we don't have only rectangles, but also irregular shapes. The first step is concluding the model for placing regular items on convex quadrilaterals, here. Then generalize the packing for general quadrilaterals. To summarize, we've proposed several contributions for cutting packing problems, but even more importantly, these approaches are new ways of looking at these problems which could serve a catalyst to even better approaches. Okay, that's it. And this brings us to the end of this presentation. Thanks for your attention, and if you have questions, you can send me an email to ask me what you need. Thank you.